Today we're going to talk about functions and relations. A relation is a correspondence between two sets. We typically call them the domain and the range. So remember, the domain are the input values and the range are the output values, such that to each element of the domain there is assigned one or more elements of the range. And what is a function? A function is a correspondence between two sets, the domain and the range, such that each element of the domain has exactly one element of the range assigned to it. In order to understand this better, let's take a look at some real life examples. The domain, Wabansie Valley High School students, and the range are integers. We're going to assign a map of the student to their age. So the question is, if we take a look at these sorts of things, a function is a special type of relation. So that means if you have a function, you are guaranteed to have a relation. But in this particular case, we have to decide, do we have a relation? And if we do, is it a function? So does every element of the domain have an element of the range assigned to it? Does every student have an age? Yes. Does every student have only one age? Yes. So in this case, this is a function. Number two, the domain are students, the range are classes. We're going to map the student to their classes. Does every student have classes? Yes. Does every student have only one class? No. So this is a relation. Number three, Wabansie Valley High School parents and guardians, range. The students, this with the parents is like matching them. So I'm sorry, I should have kept that off. The map is mapping the parent or guardian to their child or their ward, so to speak. So does does every parent or guardian have some sort of child or ward if they're associated with Wabansie Valley? Yes. Does every parent or guardian have only one? No. So then this is a relation. Keywords, range, matches from Google, or the statement no match is found. So it's going to be matched to some number that relates to how many matches they have, or um, the statement no match is found, or like zero or something. So does every keyword have a number of matches? Or no matches? Yes. Does every keyword have exactly one of those things? Yes. So in this case, this is a function. Number five, Wabansie Valley students, range, Wabansie Valley art classes. We're going to map the student to the art class. Does every student have an art class? No. Since every student does not have an art class, this is not a relation. Okay. Now, what I did was I just took 1 through 5 and I simplified them to not have like 2,000 students or whatever, but I simplified them so that we could kind of see something that relates to it. So if we're looking at number one, mapping every student has an age that's associated with them. And I could keep going for thousands of numbers, but every student has an age associated with it. So the domain in this case is 1 to 10. And the range is 14, 15, and 16. Now, the actual problem would have 1 through 2600, and the range would have 14, 15, 16, 17, 18, or maybe some 13-year-olds or something like that. But in general, that's the case in this problem. The domain here are all of the x values that you see, so 1, 2, and 3. And the range here, 3, 4, 8, 9, 10, and 34. So those are the domain and range. This is a relation because if you notice, I basically just kind of took something that's similar to number two. So mapping student to their courses. So this student has the course 10, the course 3, and the course 4, so to speak. Um, but notice that each student has more than one course. So therefore, we cannot have a function that is a relation. If we look at number 3, um, what ends up happening is this these parents have the same kid. These parents have the same kid. This parent this kid has a single parent, it looks like. But notice that these parents have more than one child. Since each parent is identified with at least one child, but maybe more than one child, then that means that this is a relation. So if I was looking at the domain here, the domain would be, in this case, 1, 2, all the way to 7, and the range is 100, 200, 300, 400, and 500. Okay, this is 1, 2, and 3 for the domain, and the range in this case is 100 and 0. But if you notice, this problem is very similar to number 4 because uh, every keyword has a number of matches, but it only has one number of matches. Uh, and then as the internet keeps expanding, that number will change. But at any particular point in time, each keyword has an exact number of matches. So that's a function. And then when we look at this student doesn't have any art classes, and we have a problem. Okay. Tell whether or not the relation is a function. One way that we can tell if a relation is a function or not is by using the vertical line test. So a relation is a function if anytime you draw a vertical line anywhere, it only hits one or less points on the relation. Okay, so like for example, if I draw a vertical line over there, that's not an element of the domain, we're okay. But if we're drawing a vertical line through any element of the domain, it has to hit exactly one spot on the relation in order for it to be a function. So this clearly does not pass because through this element of the domain, I have two elements of the range. So this is not a function, it is just a relation. I should probably write yes or no instead of that because all of these are going to be relations. Uh, yes, 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 yes. What about here? That Sorry, what about in that spot? That's also a yes because only one of those is filled in. So that is a function. Yes, 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 yes. So that's a yes. Looking here, that's a no. Looking here, this is a yes. A lot of people might get confused because there are gaps, but that's okay. All that has to happen is that every element of the domain has to have one output. So every input has to have only one output assigned to it for it to be a function. So if there are parts that are not in the domain, that's okay. We can have, this is called discrete. So something that's discrete is just a bunch of points, basically. It's not continuous. It doesn't like form a line. And then this particular case, this is also a yes. One thing that might be a little confusing here is if I draw a line here, that's hitting 2 points, but that's the horizontal line test, and that's actually determining if a function is one-to-one. That's something that we won't talk about at the moment. Okay, plot the graph of the given equation in the indicated domain, identify the range, and determine whether it's a function. Okay, so this is basically just plotting points. The domain are values of x for which there are real values of y. So the domain here is all real numbers, so negative infinity to infinity for the x's. The range is -9 to infinity. We can tell because if I start drawing horizontal lines, I end up getting a bunch of values there. So, but it starts at -9. Um, and then it goes off to infinity. This may look like the domain stops, but it does keep going forever and ever. It just slowly moves left and right forever and ever, but it does keep going forever and ever in the x direction. Okay, is this a function? Yes, because it passes the vertical line test. There's no vertical line that hits more than one value in any element of the domain. This is actually a sideways parabola. So the domain in this case looks like it is negative infinity to 3. Looks like we're never going to get past 3 for the x values. So that's kind of important to keep in mind. And then the range here is negative infinity to infinity. That is because I can basically have any value of y I want. But my x's are never going to get bigger than 3 because there's nothing that I can substitute in here that's going to make 3 minus a square end up being something that's bigger than 3. Finally, is that a function? It is not a function. It is only a relation because it clearly does not pass the vertical line test at pretty much any value of the domain except for 3. Okay, find the value of the following given these 3 functions below. Okay, so if we look at these 3 functions, we're going to just substitute some things in. So g of w, anywhere there's an x, I'm going to replace it with a w. So there's an x, I'm going to replace it with a w. So g of w is 4 minus 7w. Letter B, f of negative 3. So anywhere there's an x, I'm going to replace it with negative 3. So I have negative 3 squared minus 2 times negative 3 minus 8. Negative 3 squared is positive 9, so that's something that's really important to note. Negative 2 times negative 3 is positive 6, and then minus 8. So 9 plus 6 minus 8 is 15 minus 8, which is 7. So f of negative 3 is 7. G of negative 5 times f of 1. So I'm going to take negative 5, substitute it anywhere there's an x. I'm going to take 1, substitute it anywhere there's an x in g and f respectively, and then figure out what's going on. So g of negative 5 is 4 minus 7 times negative 5. That's g. And then I'm going to take that value. I have to find that value all together, and then multiply that by whatever happens when I substitute in 1 to f of x. So 4 minus or negative or minus 7 times negative 5 is 4 plus 35, so that's 39. And then 1 minus 2 is negative 1, minus 8 is negative 9. So I have 39 times 9. That's the same, well, 39 times negative 9, sorry. That's basically the same thing as, remember, you won't have a calculator on your test in this case. So if I have 39 times negative 9, I can kind of think of that as 39 times negative 10, which is 390. But then I have to add back a 39. So that is probably the easiest way to think about doing that one. So when I do that, I end up with negative 351. So letter C is negative 351. D, h of 2. So I'm just going to substitute 2 in. I get absolute value of 2 plus 3. Absolute value of 2 is 2, so 2 plus 3 is 5. E, f of 2 plus g of negative 4. So if I take f of 2, I get 2 squared minus 2 times 2 minus 8. Then I'm going to add g of negative 4. So that is 4 minus 7 times negative 4. So I have 4 minus 4 minus 8 plus 4 plus 28. So 0 minus 8 is negative 8, plus 4 is negative 4, plus 28 is 24. So the answer to that is 24. F of h of negative 1. So this one is a little bit of a composition. So composition of functions is what happens when I take h of negative 1 and then substitute it back into f. So h of -1 is absolute value of -1 plus 3. So that's 1 plus 3, which is 4. So what I need to do is I need to do f of 4. So if I did h of -1, that ended up being 4. That then gets substituted in where h of -1 was. So I have f of 4. So now I'm just going to do f of 4. So I have 4 squared minus 2 times 4 minus 8. So that's 16 minus 8 minus 8, and that's 0. So letter F, which is f of h of -1, ends up being 0. Finally, g of f of x times h of 3. So g of f of x, I'm going to replace this with f of x. So that's x squared minus 2x minus 8. Then times h of 3. Well, h of 3 is just 6. So I'm going to multiply by 6 at the end. Okay, so g of x squared minus 2x minus 8 means that wherever there's an x in g, I'm going to replace it with x squared minus 2x minus 8. So g is 4 minus 7x. So I'm going to replace the x with x squared minus 2x minus 8. And then all of this is multiplied by 6. So I have 4 minus 7x squared plus 14x plus 56. All of that is going to be multiplied by 6. So now it's just a matter of simplifying things. Notice that I used the distributive property here in order to deal with that. I did not do 4 minus 7 first. That's just the order of operations. So negative 7x squared plus 14x plus 60, because I added the 4 and the 56. Now I multiply everything by 6. So I have negative 42x squared plus 84x plus 360. That is g of f of x times h of 3.